Hello everyone, my name is Quentin Hérault, and today I am excited to present our work titled 3DGS-Calib 3D Gaussian Splatting for Multimodal SpatioTemporal Calibration, which I co-authored with my colleagues from Huawei, ICB, INVIA, and MIS. Robotics systems depend on multiple sensors, like LiDAR and RGB cameras, to perceive the environment. The combination of these sensors modalities improves tasks like localization, mapping, and object detection. However, to successfully fuse data from these sensors, accurate spatial temporal calibration is essential. Existing methods either require a lot of manual setup, specific features in the scene, or are too slow for practical use. This motivated us to find a faster and more robust solution. Target-based methods rely on physical calibration objects, such as checkerboards or fiducial markers, to estimate the relative poses between sensors. These approaches offer high accuracy, as the known geometry of the target provides reliable reference points for aligning sensors, but they require precise target placement and controlled environments. Targetless methods remove the need for physical calibration objects, using natural environmental features to align sensors. These approaches are more flexible for real-world scenarios, but can be less reliable in environments lacking distinct features, requiring robust feature extraction and matching techniques to compensate for the lack of explicit calibration targets. Deep learning-based calibration methods leverage neural networks to automatically learn sensor alignment from large datasets. These techniques can generalize well across various environments and conditions, making them useful for tasks requiring real-time calibration, though they depend heavily on the availability of high-quality training data and may suffer from interpretability issues. NERF, neural radiance fields, based calibration techniques utilize 3D scene reconstructions from a collection of 2D images to optimize sensor alignment. By modeling the scene's appearance and geometry with a neural network, NERF-based methods achieve high precision, especially in complex, unstructured environments. But they often require significant computational resources and careful tuning of scene parameters. This is where 3D Gaussian Splatting, or 3DGS, comes in. It offers much faster rendering and training times while maintaining high quality. This inspired us to explore 3DGS for our calibration problem. 3D Gaussian Splatting works by representing a scene with a high number of 3D Gaussians, each parameterized by their position, color, scale, and opacity. These Gaussians are splatted onto the 2D image plane using the camera's intrinsic parameters. A photometric loss is then calculated between the rendered image and its ground truth counterpart, and the parameters are optimized through gradient descent. Here, we introduce 3DGS-Calib, the first multimodal calibration method based on 3D Gaussian splatting. Compared to NERF-based method, it's significantly faster while maintaining accuracy. The method works by using LiDAR data to initialize the 3D Gaussians, which allows us to create a continuous scene representation. This representation ensures both geometrical and photometric consistency between sensors, enabling robust spatial-temporal calibration. Here's the pipeline of 3DGS-Calib. We start by inputting the accumulated LiDAR point cloud, which is downsampled using voxel downsampling. A neural network predicts the parameters of the Gaussians, including color, scale, and rotation. The calibration parameters, such as the extrinsics and the time offset, are adjusted by minimizing a photometric loss with a ground truth image. We only consider the bottom half of the image, as the LiDAR points are concentrated in this part of the images. Finally, the optimization process results in calibration for both spatial and temporal alignment. For our experiments, we use the KT360 dataset, which includes urban driving sequences with front and side cameras, as well as 360-degree LiDAR. We selected three sequences: a straight line movement, a large rotation, and small zigzags. And our evaluation metrics are the rotation error, translation error, and temporal error. We also conducted an ablation study to investigate the effects of voxel size on calibration performance. As we can see, smaller voxels allow the model to learn the finer details of the scene. However, it also causes the optimization process to get stuck in a local minimum. Larger voxels provide larger basin of convergence and shorter training time, by greatly reducing the number of 3D points for the model inference. Thus, we propose to progressively reduce the size of the voxels, simulating coarse-to-fine training process, with a balance between speed and performance. Here is a visual example of the optimization process. We can see as the voxels get smaller, the finer details get rendered. These are some qualitative results for the LiDAR to camera calibration. In these visualizations, we can see that 3DGS-Calib offers better alignment between the LiDAR point cloud and the camera images compared to the mutual information-based method proposed by Pandy et al., the deep learning method LCCNet, and the nerve-based method MOIST. On the right, we can see that MOIST is unable to fuse the geometry from the camera and the LiDAR. With the quantitative results, we can see that 3DGS-Calib outperforms MOIST in terms of both accuracy and training time. We achieved lower rotation and translation errors while reducing training time by a factor of 10. For the LiDAR camera calibration task, 3DGS-Calib outperforms Pandy et al., LCCNet, and MOIST. In conclusion, we presented 3DGS-Calib, a fast, accurate method for multimodal calibration that eliminates the need for external targets. It significantly outperforms nerve-based methods, both in terms of speed and accuracy. And in the future, we plan to improve adaptability for more complex sensor setups and expand to less common LiDAR configurations. Thank you for your attention.